Welcome back to the last lecture in our brief three-lecture theme that looks at the overall framework, the space and time within which the whole cosmological story unfolds. When I introduced this theme, I mentioned how this part of cosmology was also the first to be developed in the first third of the 20th century. So it has a rather classical, old world feel. We've had no fancy images of galaxies or big computer simulations. But I hope that despite its rather idealized mathematical flavor, you've nonetheless been able to sense the enormity of the topic. It's nothing less than the form of the infinite coordinate mesh of space stretching out in all directions, sprinkled with galaxies. Is it Euclidean, or is it curved in some way? And how is it stretching? It was hurled into expansion by the Big Bang, but will it keep expanding, or will it recollapse inwards? Now, fortunately, as we learned last lecture, the symmetry of the cosmological situation allows us to use Newtonian thinking to help understand what's going on. We looked at the expansion of a sphere of rocks and simply demanded that the sum of their kinetic and gravitational energies remains constant throughout the expansion. And lo and behold, we arrived at the same equation as a full-blown analysis within general relativity. With this framework now in place, we're ready to shift fully into the cosmological setting. My overall aim is that by the end of this lecture, you will understand why the three great eras of cosmic history, the radiation, matter, and dark energy eras, have three kinds of expansion: rapid deceleration, modest deceleration, and exponential acceleration. Most importantly, you'll see that dark energy makes the universe fall outwards rather than fall inwards, and that's why it accelerates. As before, I'll combine graphical and mathematical approaches. If you're not a math person, just let that part go. It really doesn't matter, and focus on the graphs and the concepts. In fact, I want to reassure you that the last lecture and this lecture are by far the most challenging in the course in terms of math and graphs. I deliberately aimed high because I know that some of you like this more rigorous approach. But I promise that after this lecture is over, most of the math will be behind us and we'll return to the more concrete world of atoms, stars, and galaxies with a much more straightforward approach. So having said that, I'm afraid I'm going to start off with a brief bit of math, picking up where we left off last lecture. Remember, we're watching an expanding sphere of stuff. It has kinetic energy of expansion and gravitational energy from it pulling on itself, and during the expansion, the total energy remains constant. In math terms, this is described by our expansion equation, which is called the Friedmann equation. Here are the three terms corresponding to kinetic energy, that's the v squared term, gravitational energy, that's the middle one, and on the right we have the total energy from Newton's perspective, or the curvature of space from Einstein's perspective. Ultimately, this equation tells us how the expansion velocity, v, depends on the universe's size or scale factor, s. Now remember, s tracks the separation of galaxies relative to their separation today. It's 0 at the Big Bang and increases and is 1 today. Remember also, we use a subscript 0 to mean the value of something today, when s is 1. So this first term is the expansion velocity relative to today's expansion velocity, v over v0. What about the other terms? There are three of them, and they're all densities of one kind or another. First, the term on the right, ρ0, is today's density, ρ for density, 0 for today. And below that is the critical density today, ρ0 crit. It's the density that just makes the geometry of space flat. And it's given by 3h0 squared over 8 pi g. Now remember, when we have a ratio of a density to a critical density, cosmologists often rewrite that using the symbol omega. So the right-hand side is just 1 minus omega naught. Now let's look at the middle term. It has a simple rho in it, the density at any particular stage in the expansion, not just today. So it drops as the universe expands. This is by far the most important term because, as we'll see in a minute, exactly how the density drops determines how the expansion changes over time. For example, whether it decelerates or accelerates. So let's look at this term in more detail. Here's a spherical region in our universe. It contains 3 components: matter, that's actually atomic plus dark matter; radiation, that's both photons and neutrinos; and dark energy, which we're viewing as the energy of empty space. It's a vacuum energy. To find each component's density, we simply add up however much there is in the sphere and then divide by the sphere's volume. Remember, density is mass over volume. Now, although we commonly think of both radiation and vacuum energies as energies, remember, energy and mass are essentially the same thing, so they both produce gravity. So we simply divide the energy by c squared to get its equivalent mass. So the total density is the sum of these 3 densities, rho tot equals rho matter plus rho radiation plus rho vacuum. The critical question is, how do these 3 densities change as the expansion proceeds? Here's the situation. Today, the scale factor is 1, and the component densities are rho m naught, rho r naught, and rho v naught. At some later time, the scale factor is s, so the sphere's radius is bigger by a factor s. So its volume is bigger by a factor s cubed, and the densities have changed. They're now rho m, rho r, and rho v. There's no naught. Now, what happens to the 3 densities depends on which one we're talking about. And let's take matter first. The total amount of matter hasn't changed. Within the sphere, no atoms have been created or destroyed. They've just been spread out over the larger volume. So the new density, rho m, is the original density, rho m naught, over s cubed. It's s cubed because the volume has increased by s cubed. What about radiation? The photons have been spread out, just like the atoms, but something else has happened to them. They've been redshifted by the expansion. The waves are stretched, and the energy of each photon has therefore dropped by a factor s. So the combined effect of photon dilution and redshift makes the new radiation density, rho r, equal to the original density, rho r naught, over s to the 4th. Finally, the vacuum density is easy. As the universe expands, the density of space doesn't change. Space is space. If the region gets bigger, there's simply more vacuum. So rho vacuum is constant. We have rho v equals rho v naught. So at any given scale factor, s, the total density, which we write rho of s, is just the sum of these individual terms. Today's matter density over s cubed, plus today's radiation density over s to the 4th, plus today's vacuum density. Okay, one last step. We need to insert this into the gravitational term of our expansion equation. Here it is. So we want to substitute this group of 3 in here. So we take each of these terms and divide by the critical density and multiply by s squared. Now, dividing by the critical density converts these rhos to omegas. and multiplying by s squared changes the s dependence of each term. So we now have a new, improved Friedmann equation that can handle universes with three components. It still has the three basic terms, kinetic, gravitational, and total, or curvature, but now the gravitational term has contributions from each component, matter, radiation, and vacuum. Over on the right, the sum of these omegas makes omega total, and that sets the universe's total energy, or curvature. You may find it hard to believe, but this little equation contains within it the expansion history of a very wide range of possible universes, each with its own particular mix of matter, radiation, and vacuum. The only assumptions that we've made are that the universe is homogeneous and isotropic on large scales, that the density of matter, radiation, and vacuum change with expansion the way we said they did, and everything obeys Einstein's general relativity. We call universes that obey this equation Friedmann, Robertson, Walker universes. Friedmann for his solution to Einstein's field equation in 1922, and Robertson and Walker for their 1936 spacetime that we met in Lecture 10. All the evidence to date suggests that on large enough scales, these assumptions are valid, and the expansion of the universe does indeed obey this equation. It really does seem that we live in a Friedmann-Robertson-Walker universe. Furthermore, we now think we actually know the values of the three omegas. They are 0.27, 0.000084, and 0.73, giving omega total of 1.0. It's a flat Euclidean geometry. Well, I think we've had enough algebra, so let's now bring this equation to life by recasting it in graphical form. Here's the kind of graph we used last lecture. The x-axis is size or scale factor, S. So the Big Bang is at 0, and today is here at 1. The y-axis is energy, positive upwards, negative downwards, with 0 in the middle. Here's a situation very similar to the real universe. The matter and vacuum omegas are 0.27 and 0.73, just like the real universe, but I've turned up the radiation omega to 0.05, just so that we can see its role a bit more clearly. I've color-coded matter in green, radiation in orange, and vacuum in blue. Here are the three gravitational curves with their formulae. They're all negative, of course. Each curve is scaled so that when S is 1 today, it passes through the correct omega value. So you can see them going through 0.05, 0.27, and 0.73. If you add all these curves, you get the total gravitational term in white. It has a classic hilltop shape with a steep side on the left and a gentle slope on the right. Now, I'll come back to all these shapes in a minute. Okay, now here in red is the total energy, or curvature term. It's 1 minus omega total, which of course is constant throughout the expansion. Now in this case, it's minus 0.05, so the universe has a closed geometry in this example. And here's the kinetic term in yellow. It's positive, of course. From the expansion equation, you can see that at every point, the yellow kinetic term plus the white gravitational term equals the red total term. Finally, here in dotted purple is the all-important expansion velocity. It's just the square root of the kinetic, i.e. v squared, term. Remember, the expansion velocity now allows us to go to this diagram, the size and velocity history, with time along the x-axis. For this example, the universe starts with a Big Bang, expands rapidly at first, but then decelerates until the velocity reaches a minimum. When the expansion is coasting, then the expansion begins to accelerate, picking up speed exponentially and both size and velocity zoom off up to the top right. Okay, now this is all quite intriguing, but at this point you may have lost sight of what's actually going on. So let's take a few minutes to understand this remarkable expansion. The most obvious feature is the incredible difference between the early decelerating expansion and the late accelerating expansion. Why does the expansion change so drastically? It's all to do with which of the three components, radiation, matter or vacuum, dominates the density, because that's the component that also dominates the gravitational energy term. Remember, in the early universe, radiation's density is greatest. In fact, you can see its curve here crosses the matter curve and is more negative at earlier times. That's because it has the highest density. Now, because it rises so steeply to the right, that means the yellow kinetic energy and purple velocity curves must drop very steeply. In other words, the universe must decelerate rapidly during the radiation era. Now let's move over to where the vacuum crosses the matter curve. To the right of that, the universe's density and gravity are dominated by vacuum. And because its curve drops to the right, then the yellow curve, the kinetic energy curve, and the purple velocity curves must rise to the right. So the velocity increases and we have an accelerating expansion. Okay, so now let's go to the real universe. So we'll keep the matter and vacuum omegas at 0.27 and 0.73, but we'll turn the radiation term back down to its correct omega, 0.000084. Here's the new energy graph. Most of cosmic history is determined by the matter and vacuum, with the radiation curve just visible on the left at the very early times. This is one of those instances that it helps to go to exponential axes. So here it is. All those curves turn into straight lines, and now you can really see how each component dominates for a particular portion of the expansion. Radiation before 60,000 years, vacuum after 9 billion years, and matter in between. These, of course, are the three great eras of cosmic evolution. Notice how the velocity evolution also has three quite distinct stages. A steep, rapid deceleration, then a less steep, less rapid deceleration, and then an acceleration. Let's now go to our size and velocity history curves, first using linear axes. You can see the early deceleration and later acceleration with a changeover around 7 billion years. Now, for reasons I don't have time to explain, this actually occurs a little before the density changeover, which happens around 9 billion years. But let's look more carefully at that initial expansion, roughly the first billion years, using exponential axes. The decreasing expansion velocity is in purple, and increasing size, or scale factor, is in green. And I've marked the changeover near 60,000 years between the radiation and matter eras. So, for example, 100 years after the Big Bang, any 2 points in the universe were 100,000 times closer than they are today, and they were separating from each other 1,000 times faster than today. For example, two regions at 1 million light years apart today were only 10 light years apart at 100 years. They're separating at 22 kilometers per second today, but they were separating at 22,000 kilometers per second at 100 years. As time passes, the two regions get further apart and their speed of separation decreases. Notice that as the universe crosses from the radiation to the matter era, this deceleration rate gets more gentle. It isn't as steep. As a result, the separation grows a little faster, so the green line bends up. Now, in math terms, during the radiation era, the scale factor grows proportional to the square root of time. So that's time to the half power. While in the matter era, the scale factor grows proportional to time to the 2/3 power. Now, here's an interesting property of this early period of expansion. Notice that as you go closer and closer to the Big Bang, to the left, S, the scale factor, obviously gets closer and closer to 0. But the expansion velocity gets higher and higher, and at the Big Bang itself, the expansion is infinitely fast. This is a rather remarkable feature of universes that begin dominated by radiation. And it'll play a crucial role in Theme 7 when we try to understand how inflation fits into these very early times. Now let's take a look at the most interesting phenomena here, the vacuum's amazing ability to drive an accelerating expansion. Back with our energy curves, we're looking at the right-hand side where the vacuum's gravitational energy is dropping to the right. So the kinetic term must rise to the right, so the velocity must also rise, so the expansion accelerates. This is a fascinating behaviour, but it's one thing to follow these curves, it's quite another to understand it intuitively, what's going on. And we should spend a few minutes just trying to do that. What we need to do is to look carefully at what it means to say something is falling. See, here on Earth, when I let go of an object, it falls. It gets closer to the Earth. Why is that? It's because things always try to move to a location of lower energy. By getting closer to the Earth, the gravitational field of the apple and the Earth are more enmeshed. If the object is lower, this energy of interaction is larger and more negative. In a sense, that's what lower means, the direction towards which things move. Now, let's look at a sphere with a rock at its edge. The gravitational energy of the rock is, as always, minus gmm over r, where big M is the sphere's mass and little m is the rock's mass. Now focus on the rock and consider moving it and the surface of the sphere to larger r. What happens to the gravitational energy? Now, if the sphere contains matter, then the sphere's mass doesn't change. R, however, is bigger, so looking at the equation for the gravitational energy, we find it gets less negative. So this motion is uphill, just as we'd expect. Now the opposite, to smaller r, is downhill. So that's the direction that an object, the rock, would fall. You can even see this on our energy graphs. The green matter curve slopes downwards to the left to smaller size. Put a ball on that curve, it'll roll to the left. Now consider the sphere filled with vacuum with some density. So the sphere still has a mass, which generates gravity. Just as before, let's increase r both for the rock and the sphere and ask what happens to the gravitational energy. Well, as before, r increases, so this tends to make the energy less negative. But this time, m, the mass, also increases because there's more vacuum. In fact, the total mass of the vacuum sphere is proportional to r cubed. So this is a big increase in the mass that dominates the change in the gravitational energy, which gets larger and more negative. So larger r is downhill. Now this, amazingly, is the situation. Downhill to lower energy is outwards. The universe falls outwards. This is why vacuum density makes the universe accelerate. It falls outwards freely, and with nothing to stop it, it just gets faster and faster. Again, you can see this on our energy graphs. The blue vacuum curve slopes downwards to the right, to larger size. If I let a ball go on that slope, it would roll to the right, downwards, to more negative gravitational energy. Now, so far so good, but there is one extremely important part of the story I've omitted, and indeed you may already be puzzled over it. When our sphere expanded, we have more vacuum here, in this shell. But vacuum has mass and energy. Where's that energy come from? You can't just create it out of nothing any more than you could create this podium out of nothing. The answer is that the gravitational energy liberated by falling outwards is enough to create this extra vacuum as well. Bingo! We have a self-generating, self-sustaining expansion. You see, when space actually weighs something, then it doesn't just fall outwards, making things accelerate. The gravitational energy liberated from this falling actually creates more space, the very space into which it's falling. And with nothing to stop it, the expansion could, in principle, go on indefinitely, making a bigger and bigger universe filled with more and more vacuum. When you first grasp this accelerating, self-generating mechanism, you can't fail to be stunned by its economy and beauty. But in fact, the story gets even better. See, although I've built this discussion around today's gently accelerating old universe with its very low density vacuum, this is the very same mechanism that is thought to drive a staggeringly rapid inflation of the very young universe using a much denser vacuum. Now, I've reserved 4 lectures for inflation later in the course, but I wanted to plant the seeds for that discussion now, while we're looking at the remarkable properties of vacuum energy. As we'll see, a very much denser vacuum may have existed shortly after the Big Bang. And like today's much weaker vacuum energy, the dark energy, it fell outwards, accelerating, making more of itself as the expansion continued. But because it was a much, much denser vacuum than today's vacuum, it fell outwards much, much faster, both creating and launching our current universe. Quite a stunning proposition. But you'll have to wait till theme 7 to get the full story. At this point, I'd like to return to a historical account of some of what we've been talking about, and I want to consider the birth of the concept of vacuum energy. Now, vacuum energy is in fact a thoroughly modern concept, but something very similar to it was present right at the very start. You see, when Einstein first tried to apply his theory of general relativity to the whole universe in 1917, he looked for a static solution. After all, at that time, the universe seemed vast and old and motionless. But just as your own intuition would tell you, a universe with just matter can't be static. It tends to collapse in under its own gravity. So he looked hard at his equation. Here it is from 2 lectures ago. And rather reluctantly, he reintroduced a term he'd simply set to 0 in his 1915 paper. Here it is on the left-hand side as part of the space-time geometry. It's called the cosmological constant, written capital lambda. Although it doesn't interfere with the validity of the previous equation, it does introduce what amounts to a long-range repulsive force. And by balancing this force against matter's tendency to collapse, he created his static universe. We call it the Einstein universe. In fact, in 1917, Willem de Sitter, a Dutch astronomer, removed the matter term and found the exponential accelerating expansion that we've been talking about. Now, from today's perspective, we know the vacuum is live with quantum effects, and this raises the possibility that it isn't simply void and empty, but has a non-zero, apparently tiny, density. Now, in that case, this vacuum density can be included on the right-hand side of Einstein's equation, along with the other density terms. This turns out to be identical to having the cosmological constant on the left. So conceptually, the two are rather different, but in practice, they have the same effect. So one might say, today's vacuum energy has grown out of yesterday's cosmological constant. Okay, well look, let's draw this theme to a close, and I may have already shown you one too many coloured graphs, but let's not forget that we set out to understand the nature and growth of the space and time that holds the entire universe. This is no small aim, and as far as we can tell, the concepts and methods I've outlined are enough to achieve that understanding. As I warned you, the flavour of this theme has been a little abstract and mathematical, but I hope that nevertheless your Newtonian intuition has helped you achieve some sense of why cosmic expansion behaves the way it does. With our understanding of the overall framework now in place, it's time to people the universe, to consider its contents, stars and galaxies. Although even these have their precursors, as we'll learn in our next theme, Theme 3, the first million years.